So in the previous video, we showed that that our vector space is actually a ring, and we can write it this way. So from now on, we'll write it as like this. So z adjoin root 2. Okay, as the ring that contains z and the root 2, and then the smallest such ring. Okay, so we first of all, we see that if there's an element in the ring, let's call it x, right? We can write it in the form a plus b root 2. Is it the case that a and b are unique? So if you give me an x, then I can find you an a and b, a specific a and b for which x equals a plus b. So if you don't quite understand what I mean, right? If you just think that this is what everything in here looks like, if that's a picture in your mind, what if I actually just added, for example, if one of the elements was 1 plus square root of 2, and then I instead this x equals that, right? Then the element in here, what if instead it just looked like, what do you call it, 2.414 something, yeah? Would you be able to extract the a and b back out, right? So if you type this in your calculator, you get something like this. Would you be able to extract this back out is the question. And the answer is yes, you can. And that's because of the linear independence of this. So the fact that it is indeed the 1 and square root of 2 form a basis, you are able to extract out the a's and b's, because 1 and square root of 2 are independent. They form a basis, and so every single x in this can be represented uniquely by the a and b's. That's a lot of words, but so what's next? What's next is, so in the complex numbers, just kind of inspired by the complex numbers, we want to make a z bar, so a complement of z. So if we want to see as a picture, for example, maybe if we have a along here and b down here, where x we can have, oh sorry, this is a, this is b or something, then x would be, oh sorry, it should be here. This is the one axis, and this is the square root of 2 axis, okay? And here's a and b, then this would be x. And x bar, in the same way as with complex numbers, we have x bar as in over here, as in it's reflected along a minus b. And I mean, this shouldn't seem too random to you that we would want to do this, because you've seen the Pell equations. And so what we see is that what we want is to solve the Pell equations, we want all the elements x in z adjoin root 2 such that x bar equals 1. And what we're going to do next is we want to call this x bar something. We're going to call it capital N of x. So capital N standing for the norm. If you've studied norms before, you might have seen it like this. I'm not sure why this is called a norm, because norms have to satisfy certain properties, but in our case, it doesn't satisfy all those properties. For example, this norm, usually norms like the absolute value symbol or something like that, they're always positive. This norm can be negative. For example, let's have an example. So we see that this norm, so a norm of a plus square b square root of 2 is equal to, well, from the Pell equation, because this is literally, we just wrote out the Pell equation in our fancy form. This is just a squared minus 2b squared, right? If we have b large enough, this whole thing will be negative. So what does large enough mean? Well, we can just pick it large. So this is have, I don't know, a is I don't know, even if a is 0 and b is 1 or something, right, we have that this is minus 2, so it's less than 0, okay, that's the point. So it's a negative. So we have this norm doesn't have the property that's always positive. So okay, so what does it have that makes it interesting? This is what we'll cover in the next video. Okay. See you later.